resistance. I have already talked about resistance, but now let's get to know about this resistance in depth. The electrical resistance of a conductor is dependent on the following factors. What are these factors? The cross-sectional area of a conductor. Now, if you have seen these conducting wires, it's like this. It's like this, the conducting wires. Now, this area which is within between this wire is called cross-sectional area. Now, this is not a proper rectangle or square or circle. This type of shape we call cross-sectional, and the area which is we have to determine is called cross-sectional area. So the electrical resistance of a conductor depends on the cross-sectional area of the conductor. Now, suppose the area of within this conductor is less, so obviously the resistivity will also be less. So if the conductive, if the area is less, the resistivity will be higher. If the resistivity is, let me write these equations. R is inversely proportional to 1 by A. If the area is lower, the resistivity is higher, because in lower amount of area, the resistivity might be higher. But in a bigger area like this, the resistivity will be less compared to this. See here, the resistivity is more, but here the resistivity is less. So when you increase this cross-sectional area, the resistivity decreases. But when this cross-sectional area is less, the resistivity is increased. So R is inversely proportional to the area, cross-sectional area. Now the length of the conductor. So we can write that R is directly proportional to the length of the conductor. R is directly proportional to the length of the conductor. Suppose you have this length. Suppose you have this length of conducting wire. So the amount of resistivity is within this conducting wire. It has a certain amount of resistivity, right? But when you have larger length of conducting wire, see, you have more resistivity within it. Remember the area, the cross-sectional area, or it's not changing. Cross-sectional area means this area, this cross-sectional area, this sectional area. The more the cross-sectional area has increased, the resistivity got lower. But in this region, the cross-sectional area is not changing, but the length is changing. Okay? So the length is changing. So if the length increases, the resistivity increases. If the length decreases, the resistivity decreases. Maybe in the cross-sectional area, I might not be clear to you. Let me say this again: cross-sectional area. This thing, this is how the wire looks like. This is like a circle, and this has a certain area. This is called cross-sectional area, not this entire thing. This is the area which is called cross-sectional. This portion of area of circle is called cross-sectional area. Okay? This area is called cross-sectional area. What is the difference between this and this? It has lower circle. The circle is smaller. So the cross-sectional area is smaller, it has a bigger circle, so the cross-sectional area is higher. So I think, and now about the length, what is the difference? Length, in terms of length, the cross-sectional area is similar. In both this wire, the cross-sectional area are same. This same. Okay. Now what is the difference? Difference is within the length. This has a L and this is L1, suppose. This L1 is greater than L. So we can say if the length of a cross-sectional area increases, the resistivity increases. And if the cross-sectional area increases, the resistivity decreases. Simple. The material, and another thing that is there, the material of the conductor. I mean, the material which we are using, how much resistivity or conductivity that already has. The temperature of the conducting material, because in this material, if you increase the temperature, there will be change in the resistivity, because resistance which are there already, materials are there that will start vibrating, and when it's vibrating, it will result the resistance to go higher. So temperature is a factor. Just remember this. I want to go in the details. Electrical resistance is directly proportional to length of the conductor and inversely proportional to the cross-sectional area. It is given by the following relation, that R is equal to, let's see, R is equal to, you can write L divided by A. Now what is this symbol is all about? This rho symbol. This rho symbol is the resistivity of the materials. See, I have said that material of the conductor is also responsible. So by this rho actually determines that how much, the property of the conductor, how much resistive or how much conductivity it has. Basically, it talks about the resistivity of the material. Okay, so if it is more conductive, then how would be the value of rho? The value of rho will be less if it has more conductivity, because we know conductivity is inversely proportional to resistivity. So if the conductivity is high, the value will be less of this rho, and if the conductivity is low, then the value of this rho will be higher, because the resistivity will become higher. Simple.